In today's class, we are going to see how to solve problems relating questions that have resistance in series and parallel, and also we'll be talking about Joule's heating effect and electric power. Okay, so first example that we from the discussion that we had in the last class, an electric lamp whose resistance is 20 ohm. So lamp has the resistance of 20 ohm and a conductor of resistance 4 ohm. So there is a conductor of resistance 4 ohm. Resistance are connected to a 6 volt battery. So this battery is 6 volt. This is 6 volt battery. Calculate the total resistance of the circuit. Okay. So first of all, to calculate the total resistance in the circuit, so we need to see if they are in series or parallel. As we can see, this circuit after starting has not split into two or more. So this is in series because the wires are not splitting. Like if you see this question, what happens is this wire that is coming from the battery, this splits into, as it was coming, this splits into three parts, R1, R2 and R3. So as this is splitting, we say that this resistances are in parallel. But here the wire is not splitting, it is continuous. So we say that this is in series. So resistance of the conductor of the electric lamp, let's say this as R1 is equals to, of the lamp that is given to us is 20 ohm. The resistance of the conductor, let's say the conductor resistance is R2, which is equals to 4 ohm. From the diagram, R1 and R2 are seen to be in series. Therefore, total resistance capital R is equals to R1 plus R2. So that will be equals to R20 plus 4, which is equals to 24 ohm. So 24 ohm is our total resistance. Part B, the current through the circuit. So we have the total resistance, we have the voltage. Now in series, what changes is the voltage, but what remains same is the current. So total voltage V will be equals to the total current into the total resistance. Whenever we take total of everything, then this formula holds appropriately. So from here we can say that I equals to V by R. I will be equals to V by R. So the total voltage in the circuit, or the voltage of the battery that is given to us, is 6 by the total resistance is 24. So 6 ones are 6 fours are. So we have this as 0.25 ampere. So current that is being drawn is 0.25 ampere. Now in part C, we have the potential difference across the lamp and the conductor. So the potential difference across the lamp. So we need to find across the lamp separately and across the conductor separately. In series, what happens is potential gets distributed. So this will have its separate potential difference. This will have another potential difference. And the sum of both of this should be equals to the total. So V1 potential difference across the electric lamp V1, V will be equals to, here the current is constant, so V will be equals to IR and V1 will be equals to IR1 because voltage is varying and resistance is different for different conductors. But the current, since it is in series, so in series what happens is current flowing through the circuit is constant. So this will be equals to I, we found out as 0.25 into the resistance R1 is equals to 20. 25 into 2 is 50. So 0.50 into 10 will become 5.0. So this is equals to 5 voltage. Now technically total voltage is 6 volt. So if this bulb has 5 volt, so the voltage that is left with this is 1 volt. Now let's find out using the same way potential difference across the conductor. V2 will be equals to I, R2. I is 0.25 into R2 is 4 and 0.25 into 4 is basically 1 volt. As we can see, the total voltage is again holding to be 6 volt. So our answers are correct. Okay. Moving to the next question. In the circuit diagram given below, the resistance R1, R2 and R3 have the values 5 ohm, 10 ohm and 30 ohm respectively, which have been connected to a battery of 12 volt. Calculate A, the current through the resistor, B, the total current in the circuit, and C, the total circuit resistance. Okay, so first of all, solution given R1 equals to 5 ohm, R2 equals to 10 ohm and R3 equals to 30 ohm, and the total voltage is 12 volt, that is across the battery. Now in parallel connection, what happens is the voltage remains constant. The current, since this current that is coming gets split into 3 parts, what happens is the current is splitting into I1, I2 and I3. So the current through each resistor might be different and will definitely be not equal to the total current. So I1, we know V equals to IR, from where we get I equals to V by R. So I1 equals to V by R1. So this will be equals to V is 12 by R1 is 5. So we get 12 by 5 as 2.4 ampere. I2 will be equals to V by R2, which is equals to the total voltage 12 by R2, that is R2 is given to us as 10. So this is equals to 1.2 ampere, and I3, current in the third resistor, will be equals to V by R3, that is equals to 12 by 30. 6 2s are 6 5s are, so we have 2 by 5, that is 0.4 ampere. For part B, now this is our part A, where we find the current through each resistor. Now this I got splitted into I1, I2, I3. So I should be equals to the sum of all these 3 currents, that is I1 plus I2 plus I3. So this will be equals to I1, that we have as 2.4 plus 1.2 plus 0.4. 2, 4, 4, this is 10. So in decimal 10 means 1, 2 plus 1, 3 plus 1, 4 ampere. So the total current flowing through the circuit is 4 ampere. If you are having confusion with the addition, you can add them on your own, you will still get 4 ampere. Part C, the total circuit resistance. Now we know the total voltage V is equals to the total current into the total resistance. So this will imply that the total resistance equals to V by I. So this will be equals to the total voltage that is given to us as 12 volt by the total current we have as 4. So this is equals to 3 ohm. Okay, so we found it in this way. You can also find it in this way, where we know that 1 by Rp equals to 1 by R1 plus 1 by R2 plus 1 by R3. As this is splitting, we know that this is connection is in parallel. So 1 by Rp equals to 1 by R1 plus 1 by R2 plus 1 by R3, that is equals to 1 by 5 plus 1 by 10 plus 1 by 30. This is equals to 30, 5 6 are 30 plus 10 3 is plus 1. So this is equals to 6 plus 3 9 plus 1 10 by 30. So we have 1 by Rp as 1 by 3, which implies Rp equals to 3 ohm. So we can do it either in this way or in this way. So any of the way, whichever you are comfortable, it will match. Okay, now coming to the next question. So first question we saw resistances in series. Second question we saw resistance in parallel. In the third question we are going to see the combination of both of them. Now when you look at the current flowing through the circuit, what happens is this is splitting over here. So these two are connected in parallel and they rejoin. Now this is again splitting into three parts. This is coming and splitting into three parts. So as this is splitting into three parts, so these three are connected in parallel. What we need to note over here is that this whole connection, this two is in parallel, but as a whole when we find this resistance and as a whole when we find this resistance, we see that this whole as a resistance and this whole as a resistance is connected by a same wire. So this final resistance what we get by solving this two and the final resistance that we get by solving this 3 is connected by a single wire. So since this is connected by a single wire, what happens is this, say this final resistance we get over here by solving this 2 as parallel is say Rp1, and by solving this 2, say we get the resistance in parallel as Rp2. So Rp1 and Rp2, these two are in series. So the final resistance that we'll get is by adding this, whatever final we get, plus this, whatever final we get. So the finals if we add, so we'll get the total resistance. Okay, let's see how to solve this. So solution, part A. Here R1 and R2 are in parallel. Therefore, Rp1 will be equals to 1 by Rp1 equals to 1 by R1 plus 1 by R2. Since this is resistances in parallel, 1 by R1 is given to us as 10 plus 1 by R2 is given to us as 40. So on solving, LCM is 40, this is 4 plus 1. So which implies 1 by Rp1 is equals to 5 by 40, 5 8ths, which implies Rp1 equals to 8 ohm. Now this 3 are in parallel, as this circuit that is coming, this is splitting into 3 parts. So as this is splitting, as this is coming and splitting into 3 parts, so this 3 are in parallel, we say this as Rp2, say here R3, R4 and R5 are again in parallel. So therefore 1 by Rp2 equals to 1 by R3 plus 1 by R4 plus 1 by R5. This is equals to 1 by 30 plus 1 by 20 plus 1 by 60. So the LCM here is 60, 2 plus 3 plus 1. So we get 6 by 60. So this implies Rp2 is equals to 10 ohm, because we'll take the reciprocal to find RP2. Now RP1 and RP2 are in series. Therefore, total resistance capital R will be equals to RP1 plus RP2. So this is equals to 8 plus 10, which is equals to 18 ohm. So this is how we get the total resistance when there is connection, two connections that are different series, and this connection and this connection are connected in parallel. Okay. And for part B, we need to find the total current that is flowing. So total current I will be equals to V by R. The value for the battery's voltage that is given to us, total voltage, is 12. By the total resistance that we got is 18. So 6 2s are 6 3s are 2 by 3 turns out to be 0.666 and dot 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 ampere. Since repeating we are getting number, so what we'll do is we'll round it off and we'll write it as 0.67 ampere. Okay, so these are three questions that are solved for you. You will solve all the questions that are there in the book and I'll check them if you have done it right or wrong. So, very important point to note over here is that which connection is better? Is series better or is parallel better? So, and which one do we use in our home? So, when we look at our home, the first thing to note is that different appliances have different current requirements. A geyser, for example, may require much more current as compared to an electric bulb. So since they require different currents, and in series what happens is the current flowing through the circuit is constant. So series connection does not make sense in case of a situation where we take a home as an example. So first note is that it is impracticable to connect appliances at home in series because each gadget has a different resistance and requires different current to operate properly. Second point is that what is another very important disadvantage of connecting in series is that what happens is, suppose we take a series connection like this. So suppose if there is a fault in this appliance, so what happens is with a fault in an appliance, the circuit is broken. With the circuit broken, there will be no current flowing through the circuit. So this bulb will also not work. So here we have only two appliances. Since both are not working, we'll check each one of them and whichever is faulty, we'll just replace it. But think of a home. When you are in a situation like where you have to check a faulty device in a home and every appliance in your house is connected in series. So we cannot keep on going checking each and every appliances to find which one is the faulty one. So that is why connection in series does not make sense. Okay. Another major disadvantage of a series circuit is that when one component fails, the circuit is broken and none of the components work. Since no gadget will be working, it becomes a Herculean task to find out which one was the faulty one. Okay, so these two are major disadvantages of connecting our resistances in series. That is why, as a result, we connect our devices in parallel. If you are asked for a third point, you can add this, that resistance in series, what happens is the value increases. As we see over here, we had 4 ohm and 20 ohm. So the total resistance that we found out was 24 ohm. They added up, it increased. But in case of parallel connection, see individual, this were 5, 10 and 30. But the total when we see when connected in parallel is only 3 ohm, less than each and every one of them. So as we can see, what happens in parallel connection is that the resistance decreases. So that is why that is another advantage of having connection in parallel. But the major two advantages of connecting in parallel are these two. Okay. Next topic that we are going to begin is the heating effect of electric current. Okay, so we know that power is equals to work done by time. Power is defined as the rate of doing work. From class 9 we already know this. Now power is work done by time. So we also know that voltage V is equals to W by Q. We discussed this earlier, that voltage or the potential is equals to work done per unit charge. So this implies power will be equals to work done equals to V Q by T. What we can do is we can mention as W equals to V into Q. This is a rough work. This is just for your remembrance, that potential was equals to work done per unit charge. So this implies power equals to work done into Q by T. Now charge per unit time, how much charge flows per unit time, is basically the current that flows through the circuit. So P will be equals to V into I. So power is equals to voltage into our current flowing through the circuit. So this is a formula for power. But what is our main motive over here is to find the heating effect. Now what is heat? Heat is energy. So instead of finding power, what we need to find is the energy. So energy is basically the amount of work done. So heat produced H in time t, H will be equals to power into time. So how much power is there and for how much time it runs. So power is VI and into time. So this is the heat produced. Now basically we have three things here: voltage, that is the potential, the current, and we have resistance. So out of these three things in our houses, now we see that what is in which connection are we doing it. We are doing it in parallel connection. So series is not very feasible, so that is why in our homes what we do is parallel connection. And in parallel connection, what happens is the voltage remains constant. As voltage remains constant, it is not a variable here. So voltage remains constant. So what we do is we remove V as equals to IR. So what we get, so this implies H equals to I square RT, where resistance varies because the number of appliances that we use in our home vary. Sometimes we use a different number of appliances, sometimes less, sometimes more. So resistance varies. The current varies depending upon how much appliances are on. The current will vary as it is in parallel connection. Now time also varies. That is why the heating effect that is produced depends upon three major factors: the current, the resistance, and the time, not the voltage, because the voltage that comes to our home is constant as all the connections are made in parallel. So H is equals to I square RT. From here we derive the Joule's law of heating. What the Joule's law of heating says is that the law implies that the heat produced in a resistor is, number one, directly proportional to the square of current for a given resistance. Number two, directly proportional to resistance for a given current. And number three, directly proportional to the time for which the current flows through the resistor. Okay, this is our Joule's law of heating. Basically, we are writing this in terms of words. the heat produced is directly proportional to the square of the current for a given resistance. The heat produced is directly proportional to the resistance of the circuit for a given current, and the heat produced is directly proportional to the time for which the current flows through the resistor. So this is how Joule's law of heating. Okay. Now we'll look at some applications over here as note. So first important point is that the electric bulb the electric heating is used to produce light as in an electric bulb. Now, how does that happen is the filament, we know that the bulb has a filament. So the filament retains as much energy. What energy is it? The heat energy. So the filament retains as much of heat generated as possible. So it gets very hot and emits light. It should not melt at such high temperature. It should not melt at such high temperature. Since it reaches very high temperature, so we need to use something that does not melt at high temperature. So a strong metal with high melting point such as tungsten is used to make bulb filaments. The second important application, first important application was electric bulb. The second important application is electric fuse. So how and why is fuse so important? So fuse protects circuits and appliances by stopping the flow of any unduly high electric current The fuse is placed in series with the device. A simple reason for why it's placed in series with the device is that, look at this circuit. Suppose if I place a fuse over here like this, so what happens is there is extra current flowing through the circuit, this fuse breaks, but still the current will flow through over here. So a fuse would make no difference. That is why a fuse is placed in series say I place a fuse over here. So if suppose this generates a lot of current, what happens is this fuse will melt and there will be no current passing through the circuit. That is why fuse is connected in series. So the fuse is placed in series with the device. Now, why does that happen? Is because it should not allow the current to flow through the circuit. It consists of a piece of wire made of a metal or an alloy of appropriate melting point. Okay, the melting point is taken in such a way that since heat produced is directly proportional to the square of the current, so if the current increases, what happens is the heat is increased. So with the heat production increasing, what happens is the circuit will break because the fuse will melt. The wire that is there in the fuse will melt. So it is made up of a metal or an alloy of appropriate melting point, and if a current larger than the specified value so if a current larger than the specified value of the fuse flows through the circuit, the temperature of the fuse wire increases and this melts the fuse wire, which breaks the circuit. Okay. Now the final topic, that is the electric power. So we already saw that P is equals to VI. Now if we replace V as IR, so P will be equals to I square R, and if I replace I as V by R, then it will become P equals to V square by R. So P equals to VI we already saw, P equals to I square R, this also we saw, as V equals to IR, and in this if we replace as I equals to V by R, so since this is V by R, so V square by R square, and the square and this R cancel out, we get V square by R. So we have three formulas for power. Power equals to I square R, power equals to V square by R, and power equals to VI. So all these three formulas for power is fine. So common or commercial unit of electrical energy is See, energy is power into time. So power, we use the unit kilowatt. The unit of power is watt, and we use kilowatt because it gives a higher power to the given appliance. Because generally when we work with appliances, the power required is on the higher side. That is why we use kilowatt for power, and for time we generally use hour. So power into time we get as energy. So commercial unit of electrical energy is kilowatt hour. We'll convert this kilowatt hour into joules and see how much it turns out to be. So 1 kilowatt hour is equals to 1 kilowatt means 1000 watt into 1 hour is 3600 second. So we have 3.6 into 1, 2, 3, 4, 5, 6 zeros. So 10 to the power 6 watt second. Watt is basically joule per second into we have second. So second cancels off. We have this is equals to 3.6 into 10 to the power 6 joule. So 1 kilowatt hour equals to 3.6 into 10 to the power 6 joules. Okay, now look at some examples and we'll conclude our chapter. So first one, an electric iron consumes energy at a rate of 840 watt when heating is at the maximum rate. And 360 watt when the heating is at the minimum. The voltage is 220 volt. What are the current and the resistance in each case? Solution. So part A, what is given? First of all, let's write that. So we are given that the voltage is 220 volt. So let's take part A where the voltage is maximum. When heating is at the maximum rate, power is 800. Power was given to us as 840 watt. So we know P is equals to VI. We need to find current, so we'll use this formula. So this implies I equals to P by V. Power is 840. Pi we have 220, 0 to 11 to 42. 11 C's are 33. We have 9 in hand. We put a decimal. We get 90. 11 8's are 88. We have 2 in hand. 0. 11 1's are 11. 9 in hand. Again comes 0. So 11 8's are 88. So 3.818. Since we are finding current, this will be in ampere. And for part P, when heating is at minimum rate power is given to us as 360 watt. We know P equals to VI, which implies I equals to P by V again. So from here we get power as 360 by the voltage as 220, cancels off 11, this is 18, so we get 11 ones are 11. We have 7 in hand, we put a decimal 0, that we get 70. 11 6 is 66. 4 in hand, we put a 0. 11 3s are 33. We have 7 in hand, 70, so 6 again. So 1.636 ampere approximately. Okay. Next example. 100 joule of heat are produced each second in a 4 ohm resistance. Find the potential difference across the resistor. Solution. So H given to us is 100 joule. Then another thing that is given is the resistance as 4 ohm. So and the time given to us, since this is each second, so time is 1 second. We know by Joule's law of heating, H equals to I square RT, which implies 100 equals to I square into 4 into 1, which implies I square equals to 100 by 4, that is 25, which implies I equals to 5 ampere. So therefore V equals to IR, which is equals to 5 into 4, that is 20 volt. So our voltage's value is 20. Two more examples. An electric bulb is connected to a 220 volt generator. The current is 0.50 ampere. What is the power of the bulb? Okay. So what is given to us is voltage is 220 and current is 0.5. So voltage is 220 volt and current is 0.50 ampere. So therefore power is equals to VI. So V is 220 into I is 0.5. So we get 110. Power unit is watt. Since we have taken both the SI units, power's unit will become watt. The last example, and with which we'll conclude the class, an electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at rupees 3 per kilowatt hour? Question mark. So, solution. So, total energy consumed is equals to, energy is basically power into time. So, that will be equals to, power is our 400 watt and time. So 8 hours every day for 30 days. So 8 into 30. So power was in watt, time was in hour. So we have 8 3 24. 24 into 4 is 96. 1 2 3 zeros. Watt hour. So to convert from watt hour to kilowatt hour, what will we do is we'll divide by 1000, because kilo is a bigger unit than watt hour. So kilowatt hour is bigger, so we divide by 1000 to convert into kilowatt hour. 0 0 0 cancels off, we get a 96 kilowatt hour. So rupees 3 per kilowatt hour, and the total units was 96. Therefore, cost of energy will be equals to rupees 3 into 96, that is equals to rupees 6 3s are 18, 90 27 plus 1 28. So we have 288.00 rupees as our cost of energy. So with this we conclude our class. Thank you.